So the midterm is coming up soon. I don't believe it. Where's time going? We're kind of halfway to the midterm. So the first assignment is due Thursday. It was posted last Thursday. We pretty much covered all the material you need for this problem set, I think. I think in section you've been discussing some of the stata and the other tools that you need. Okay, so you got another couple days there. A couple people have been asking me questions, but hopefully it's reasonably straightforward. Any questions or comments before I get started? Yeah. Oh, thanks. Oh, thanks. Were you there? Oh, great. It was a lot of fun. I was really nervous. It was like huge theater, but it was cool. So, sorry? Oh, yeah. They're going to post it in 2 or 3 weeks. Yeah. So I don't remember what I said. I was so nervous, so I want to see it too. I hope I didn't say anything too crazy. But thanks for coming. For those of you who came. Great. Okay. So let's get back into it. Before jumping back into the deworming experiment, which we were talking about, I wanted just to kind of step back and give a little bit of background. I was talking last time about the use of randomized experiments. And I mentioned how this is sort of a new tool the last 10 or 15 years. I actually ran across some data on this, which I thought would be kind of interesting for you guys just to see how things have changed in terms of research methods. So the really the earliest experiments in development economics, or some of the earliest ones that we know of, started in Kenya in the same place as the deworming study in like 1995, 1996. The deworming study started in 98. We started doing the piloting work in 97. And it was one of the first, I think, 3 experiments in development economics, the deworming experiment that we're talking about. But there's a really neat map that people at the MIT Poverty Action Lab put together. So let me just write it down. So there's the, hold on. MIT, it's called the Jameel Poverty Action Lab, JPAL, that they put together. And it's the Poverty Action Lab is a big center that is really focused on the use of experiments and randomized controlled trials in development economics. And they work closely with the center here that I'm part of, SIGA. So they created this map, which is pretty cool, which says when the Poverty Action Lab was founded in 2003, there were 7 affiliates, 7 faculty who were affiliated with the Poverty Action Lab. I was one of those 7. And we had worked on 40 studies by that time using experimental designs. And you can see a lot of them were in Kenya. So there were a whole bunch that we had worked on in Kenya, and some other research that worked on. There were a couple Dean Carlin had worked on in South Africa and Peru. Michael Kramer had done one in Colombia. There were just like some scattered experiments in particular countries. And then there were a bunch that Esther Duflo and Abhijit Banerjee had worked on in India, and these are some of Dean Carlin's in the Philippines. So there were just sort of little clusters where each of us had set up some particular studies. By 10 years later, in 2013, the number of these randomized experiments just within the Poverty Action Lab network plus the SIGA network, because we collaborate a lot, so we kind of add up numbers, looks like this. So you go from 40 experiments in really just a few clusters where we had field sites, like Busia, Kenya, where the deworming study was, to 492 studies, 126 affiliates between our 2 networks. SIGA has about 50 affiliates, and then there's 70-something or 80 affiliates in the Poverty Action Lab. And really all over the world. So now we kind of filled out so many different countries across so many different sectors. So the different colors on the left show all the different areas where research has been done. And these are just the affiliates of these 2 academic networks. There's also hundreds more randomized experiments that have been carried out by the World Bank, by different development banks, by nonprofits, et cetera. So it's gone from something that in 2003 was this really new thing that only a few people were doing, there were like 7 of us doing it actively, to something where there's hundreds of researchers using these tools to study everything in development. And so there's been a huge change. And so what's kind of neat about the deworming paper that hopefully you guys will gain from is that people have told me the deworming paper was the first of these experiments published. There were several of these early experiments published in 2004, but it was certainly one of the first group of development experiments published. And so it was kind of at the beginning of this trend that's really spread through development economics. But even beyond development economics, these tools have then spread into many other fields. So so here's what I just said about the deworming study being one of the first studies and how there's so many more going on. But now people in labor economics, public economics, political scientists, people in other social science fields are using these same tools that we've been kind of refining in development economics. So it's been exciting to be part of this change, which is one of the biggest changes of research methodology in the social sciences over the last maybe 20 years. So there were almost no experiments of this kind when I was in grad school 17, 18, 19 years ago. And now there's tons of them. So this is something that I think you guys are just going to take as normal. But when we started doing them, people thought it was crazy to do experiments. Maybe you still think it's crazy. So that's just a little bit of background about what's changed. And again, to some extent, it's neat to see some of the early experiments because they've had this influence, I think, on some of the later work. Okay, so back to the deworming study, where I already went through this. We had 75 schools in the study, and they were ordered in a particular way by geography and size. And then we counted off, as I talked about last time, into these 3 treatment groups: group 1, group 2, group 3, group 1, group 2, group 3. And those different groups received deworming at different times. So the schools that happened to be placed in group 1 started receiving treatment right away in 1998. The group 2 schools started receiving treatment in 1999, and the group 3 schools started receiving it later. So there was this kind of phase-in design. And this produced a map, which I think was the last slide I showed at the end of the lecture last time, which is really just the sort of geographic scattering of all these different schools. We're going to come back to this map a couple times later in the lecture day. And next time, what you can see if you just kind of glance at the map is, the groups 1, 2, and 3 schools are all mixed up. Sometimes they're kind of clustered together, sometimes they're all mixed up, and that's just because they were randomly chosen. It isn't like one whole area was all group 1 and one whole area was all group 2. Within any subregion, you see all groups of schools kind of intermixed. And that's really good because you might think for some reason geography could correlate with some unobservable. We've been talking about omitted variable bias. Maybe the schools by the lake are just different than the schools in the interior for some reason. Like these are fishing communities. Well, there's group 1, 2, and 3 schools all kind of scattered along the lake. Things like that. And another thing to point out is basically this district is right on the border with Uganda, which doesn't really matter much for this study, but I think next lecture I'll tell you about a follow-up study where we try to look at the longer-term impacts of deworming on these kids' life outcomes. And there it matters that we're near the border with Uganda because we've had to send our survey teams into Uganda to survey people. A lot of people in this area moved to Uganda. The sort of dominant language group and ethnic group in this part of Kenya is the same as the dominant ethnic group on the other side of the border in Uganda. So a lot of people go to study in Uganda, or they get married and they move to Uganda. They're kind of bouncing across this Kenya-Uganda border. In fact, there's a famous politician from Funyula. He was vice president of Kenya, and his brother, who had also been born in Kenya, had moved to Uganda and become a cabinet minister in Uganda, which just tells you something about how fluid, in some sense, the national identity was right on the border. Yeah. Yeah, there definitely was, and that's a really great question. It's something that we kept track of. I'll talk more about the data we collected, but we were concerned about that. We kept track of where all the kids moved every time we went to a school. And I think the concern would be, what if certain types of kids all said, oh, I really want to go to group 1 school. They're getting the deworming drugs, and their parents, maybe the parents of the kids who were just very health conscious or academically conscious moved all their kids into the group 1 schools. That would be a problem for us potentially.
So I was thinking about, just as in the process of the study, say you deworm 1 school,
Yeah, we're going to talk a lot about that. So we're going to talk a lot about spillovers across schools. There was also this possibility of movement across schools, which we tracked. And to our relief, from the point of view of the research, we found that the flows between groups 1, 2, and 3 schools were symmetric. So we didn't find any evidence of this kind of systematic sorting towards the treatment schools. And the flows over the course of a couple of years were relatively small. So we tracked that. But in terms of the cross-school effects, I'll talk about that later on today. If I don't get to it today, I'll get to it on Thursday. Does anything? So that was an observation based on looking at the map. Any other kind of thoughts just looking at the map about the setup or the setting? Okay, so let's go on to the results. We went through this equation last time when we were focused on the effect of a worm infection. There's been a subtle change to the slide here, which is instead of having W as the key explanatory variable, now we have T. T is an indicator variable, a dummy variable, 0, 1 variable, for being a treatment school. And so what we're getting when we get B here is not the effect of being infected, it's the effect of getting treatment for infection. Now those are obviously very highly correlated. Remember, there's a 90-something% infection rate in these schools. So almost all the kids are infected to start with. And when you get treated, your infection rates fall a lot, as I'll show you. So T here is almost like, it's similar to -1 times that W term we saw before. It's not exactly the same though, but it's something like that. Other than that, the other terms are very similar to what we had before. So this should look exactly like the equations we went through last Thursday when we went through the algebra around omitted variable bias. Now here, the kind of bias we're concerned about is there a systematic difference in the x's, in the sort of unobserved characteristics of the people who choose to get treated, T equals 1, versus those who don't choose to get treated, T equals 0? Are there just systematic relationships between certain characteristics and the decision to seek help-seeking behavior? We think in reality there are such things, and that's why the experiment can help us here. The experiment helps us here by breaking the link between the x's and your treatment status. Once we've randomized treatment, there's no connection between your x's and the treatment status. It's as good as flipping a coin, basically. Okay, so just going through literally exactly the same equations as last time, but substituting out W, putting T in instead of W. And hint, hint, as you've seen from the problem set, this is the exercise for the problem set. Very similar, I'm told. Some say. So what we want to do here is compare the treated T equals 1 group, the average outcomes, expectation of Y for T equals 1, the average outcomes for T equals 0. And if we don't have randomization, we're in the same situation we were in before. Whatever we're estimating is the combination of the real effect of treatment and any omitted variable bias, or what's called selection bias, meaning the types of people who select into getting treated may be different from others. Their average X's differ. So the way we can solve this problem, again, just reviewing from last time, is either A, we can collect data on the X's. That may be hard to do. 2, we don't have the problem if there's no omitted variable bias to begin with. We can't test for that, so can't assume it. That's number 2. But then number 3, and this is the solution we're getting at with the experiment, is with a randomized experiment, we can be quite confident that this condition holds. That the unobserved characteristics, basically, the people who are getting treated and those who are not getting treated are the same. There's no reason to be systematically different, so that omitted variable bias term goes away. Okay, so back to this equation, basically, the difference term here is just 0. This is what the experiment buys us, is basically this condition here. And once this goes away, we're left with the true effect. Okay, let me pause for a second. This should be a review from Thursday, but in case there's any questions or thoughts on interpretation. Yeah, that 0 there is the difference in the average omitted variables of the treated and the untreated. And in an experiment where you randomize who gets treatment, there should be no reason why those are systematically different, because it's like you flip a coin. Whereas if you don't have an experiment, and certain types of people can afford treatment or decide to get treatment and other people can't, or some people are really health conscious, other people, people aren't, then that term won't be 0. There'll be some systematic differences between the treated and the untreated. That's really the key idea. So let me just make one point. I wasn't going to talk too much about this, but let me just mention there's this distinction that's often made in the literature between what's called internal validity, if you guys are familiar with these terms, versus external validity. And we've kind of alluded to this, but this 0 term here is really the condition for internal validity. By internal validity, it means within this population we're studying, there's no systematic bias. We're left with B. The external validity issue doesn't have to do with unbiasedness within your sample. It has to do with how representative the sample you're working with is of some larger population. So in the case here in Kenya, we're studying an area in Western Kenya with very high worm infection rates. This is an area that was chosen precisely because there are so many worm infections. And the question is the B that we're estimating in some way representative or not of what the treatment effect would look like if we did deworming somewhere else? So for instance, if you gave deworming drugs to a population where there were no worm infections, you would guess, probably, hopefully B would be about 0 if there were no worm infections. It'd be kind of weird if there were a big treatment effect, unless deworming drugs do something else, right? But in a place with lots of worm infections, B should be greater than 0, hopefully, if the drugs work. Yeah. Sorry, say that again? Yeah. When we collect information, we get fewer, you mean? Or I'm a little confused. You're saying, okay, let me go back to the last slide. Okay. Okay. So better data collection reduces omitted variable bias. Okay, what I mean by fewer X's is the following. You're right, my language here isn't very clear. Imagine there's many different unobserved variables. Let's say there's 10 of them. Those are the X's, all these unobserved characteristics that may correlate with treatment. So if we collect data on 5 of those 10, we can control for them in the regression. We have data on them. They're no longer unobserved. Now there's only 5 unobserved variables left. So what I'm saying is when we collect data, we have fewer X's. What I mean is, you're right, it's confusing. What I'm saying is when we collect more data, there's fewer unobservables left. Sorry, the language is a little unclear, but because we can directly control for those in the regression. By the X's here, I'm referring to things we can't measure. So the more we measure, the fewer variables are left kind of omitted. Does that make sense? Okay, sorry for being unclear. Yeah. Yeah, so I showed you some of the stats before where there were a lot of places with 30, 40, 50% infection rates, but fewer have 90% infection rates. So this is a place with like high levels of worm infections for sure, with 90% infections. So it was chosen because the worms are a big problem there. Now, to the extent that the effects scale up in some natural way, like if you have half as many worm infections, maybe the treatment effect is roughly half the size or something, then maybe we can make some guesses about what the effects are elsewhere. But it'd be even better to do research in those different settings and really plot out what the treatment effects are. So that's the external validity issue. If you sort of run a study in an area where a certain issue is a big problem, and then you try to port those results somewhere else where it's less of a problem, maybe you'll have different results. And that's been one of the key issues that's been raised about experiments, but it's actually true of any data. even if you're not using experimental design, if you have data on a particular subpopulation of interest, you don't know in advance how generalizable your results are to another population. You can make guesses. You could say, well, people in another population have very similar characteristics, so I think the results will be similar. But the solution to that problem is actually to collect more experimental data so you can test whether the impacts are the same elsewhere. Okay. Once we had, just going back to the deworming experiment, once we had done the randomization, set up these different groups, we started collecting data. We collected baseline survey data. This is just a photo of a survey being administered on paper. Of course, now everything's collected on netbooks and tablets and stuff like that. But so this is an enumerator, a surveyor collecting data on baseline characteristics. So before the study starts, what do these different populations look like? Now, one of the things that a lot of researchers do, even though it's not strictly necessary, is when they start a project, they collect very rich baseline data to kind of check that the treatment groups and the control group actually do look similar on different characteristics. People call it a randomization check. Like, okay, we think we randomized appropriately. We think these groups should all look pretty similar. And if so, then when I collect data on all these different characteristics about them, they shouldn't look radically different. If they look radically different, you'd be concerned that you somehow screwed up the randomization in some way. Now, in some ways, it isn't strictly necessary to do this, because if you believe in your randomization, they should be balanced, right? But it's typical to do these kinds of checks. So this is one of the things we did. At baseline, we collected data for group 1 and group 2 and group 3 on a bunch of characteristics. And what I'm going to show you here are the average values for some socioeconomic characteristics, health characteristics here. And where I say n equals 25, that's because there were 25 schools in each group. Any questions so far? Is the rationale for doing this? Does it make sense? Okay. So a couple things we checked. First, do you have a latrine at home? Okay, we discussed this issue. We discussed how having a latrine, very few people in this sample in rural areas at this point in time, even today, have an indoor toilet if they have access to sanitation at the latrine, like an outhouse. And a latrine, latrine coverage is important because we mentioned how basically the worms are spread through infected fecal matter. So you might think places with fewer latrines would in general have more of these health problems. So two things to notice in that first slide. First, latrine coverage is very high. Over 80% of households have a latrine. This is much higher, for instance, than in many South Asian rural settings. In rural settings in India, typically latrine coverage is much lower. I'm not sure exactly why, but that's the pattern. What do you see in terms of differences across the groups? They look really similar. They're within a point of each other. And of course, just because we're kind of randomly sampling different groups, the averages are going to be slightly different. If we had an infinite sample and we randomly sampled, then we would think they'd be exactly the same. But with any finite sample, there's going to be a tiny bit of sampling variation, it's called. But they look really similar, basically here. The second row is, do you own livestock? So livestock here could be cattle, it could be goats, it could be pigs. There's different livestock that families own. And in this part of rural Africa, as in many parts of rural Africa, livestock are a very important source of wealth. People, when they have extra cash, will often buy livestock. And then you can sell the livestock later. You can drink milk from the cow. I mean, there's all kinds of things the livestock gives you. Here again, about 2/3 of the households own livestock. And what do you see about the pattern across the groups? Kind of the same. It's almost exactly the same across these different groups. If you look in the optional paper for this week, which is the full published paper, we have a table with 15 of these characteristics. And we just kind of go through and show how similar the groups look on these characteristics. There's also some health and education characteristics we have. So we have a report from children about how sick they are. So the kids in these elementary schools range in age from, say, 7 to 16. Elementary school is 8 years in length in Kenya, and people very often repeat grades. So you have teenagers, actually I think from 8 to 17, something like that in the sample, the bulk of the sample. And these folks are asked, are you sick often? That was one question, the one I think I have here. We also asked, in the last week, were you sick? What did you have? Did you have a fever? Did you have different symptoms? Across those different measures, about 10% of the sample say they're sick often. But again, the numbers look very similar in the three groups, maybe a little lower in group 3, but it wasn't statistically significantly different. They basically look quite similar. And then finally, the last measure here is a pre-program exam score. And let me explain how this data is constructed, because we're going to come back to this when we talk about education. When education researchers use test score data, they typically like to normalize it. Why do they do that? Well, there's some people who are like really, really tough graders like me, where the average on a test may only be like 10 out of 100 or something like that. Something like really, really low. I'm just joking. Okay, wake up, wake up. Everybody's like, what's the drop deadline? No, I'm just kidding. There's some people who are easy graders like me who have very high means on tests, 95, 98 out of 100. And then there's some people who have very low means on tests. But there's a lot of variation across tests. And you don't necessarily want to say that, just because one test has a mean of 60% and the other's a mean of 80%, that there's something meaningful about those differences. What you often care about is, in a given population, what is the distribution of test scores? And usually it has that kind of normal shape or bell-shaped bell curve. So what education researchers do is they normalize the data so the mean in any population is 0, and the standard deviation is 1. That's completely the norm in education research, economics of education research. And what that allows you to do is basically say, okay, if I'm comparing the impact of a certain intervention on a test score, I'm going to compare in terms of how much that moves me within that distribution of the population. So if it moves me, 1 standard deviation, that's more meaningful than saying it moved me, 5 points on a test. Because for one test, if it's, if the test was out of 20 points versus out of 100 points, what does 5 points mean? So this is just a way to make test scores comparable across different settings. And we did that with the test here. So the mean is 0, the standard deviation is 1. The kind of rule of thumb in education research is any effect that's less than maybe 0.2 standard deviations or 0.3 standard deviations is not very large, somewhere in that range. If you have an effect of a program of greater than 0.2 standard deviations or greater than 0.3, that's considered like a pretty big effect, like a meaningful effect. But a difference of like 0.1 of a standard deviation or less is seen as not being too big a deal, basically. So what we have here is, on average in group 1, the group 1 schools are actually slightly weaker academically at baseline. You see their average is slightly negative.